Hey, hello, welcome to the Theoretical Computer Science seminar. Today we have Marthe Bonamy from Bordeaux. Marthe is a leading figure of the graph theory and combinatorics community in France. She is a very prolific author, and she was supposed to speak about graph recoloring, and I believe this is a somewhat more specific topic today, exploring the space of colorings with Kempe changes. So we are, yeah, please.
Thanks a lot, Bartek and Kat, for the invitation and introduction. So yeah, I'm going to tell you about graph recoloring, and I don't think it's that much more specific, but we'll see what you think of it at the end of the talk. So yeah, let me start with the basics, and then we go deeper and deeper until everyone is tired of the talk. So we're looking at graphs, and just to make sure none of my theorems further down the road are false. Whenever I say graph, I mean connected graph, because we're just doing coloring. So if you have more than one quantity component, you can just like handle them separately, and it makes for nice statements to just say everything works unless this graph is specifically this, and say unless one connected component is like this or like that, and so on. So yeah, every graph in this talk is connected, and every graph in this talk is super simple. So no orientation, no weights, no multiple edges, nothing. And like usual, we should color. You just call vertices so that adjacent vertices receive different colors. But I'm not here to tell you about coloring. I'm here to tell you about recoloring. So, I mean, as Bartek kind of implied in the introduction, you have different ways to change a coloring. But I'm interested in a notion of change, which is that of Kempe change. So what's a Kempe change? You take your two favorite colors, say your two favorite colors are green and blue. You look at the subgraph induced by these two colors in the graph, I mean, given the current coloring. You take a connected component, so I mean, here you don't have a choice, like that's just this before, and you swap the two colors there. So you get this coloring. So more formally, I mean, you have the more formal definition at the bottom. So you pick two favorite colors, look at in the subgraph, take a component there. That's a Kempe chain, and a Kempe change is when you swap the colors. So we're just going to keep executing Kempe changes. So let's give another example, just to make sure we're all on the same page regarding what's a Kempe change. So let's pick now two new favorite colors are red and green. So now when you look at the graph induced by red and green in the initial coloring, you have two components. You have this edge on the top, and you have this vertex alone on the bottom. So if you choose the edge on the top, you can swap colors, you get this. So you see this green vertex on the bottom is not impacted. And similarly, if you don't choose the top edge, but now you choose just the bottom vertex, so it does not have any neighbor called red, but that's not an issue. We can still swap colors. So it just means you change its color. So actually, when Bartek said there were other ways of recoloring graphs, that's the main other way. So you allow only this kind of Kempe change, when we recolor vertex to a color which does not appear in its neighborhood. So that's much more restrictive. And I mean, you can say also lots of things about it, but I mean, feel free to ask me questions about that at the end. But for this talk, I'm just going to talk about Kempe changes. There's more than enough things to say about Kempe changes for now. So let's go back to this graph. So you have C5, and I mean, you have all three colorings of C5. And I think you can convince yourself, well, I hope you can convince yourself that you can go from any three coloring of C5 to any other through a series of Kempe changes. I mean, you can see you can change, I mean, you can already reach quite a lot of colorings just with one step, and it's not very hard to check, that you can go everywhere. So just to say a few words about why do we look at Kempe changes, like where do they come from? Why are they called Kempe changes? So as you can probably guess from the name, they were introduced by a guy called Kempe. And that was actually a long time ago, like 1879. And the reason why he introduced that was, well, as most things in those times, was trying to prove the four-color theorem. So it did not work directly. I mean, he thought he had a proof, but the proof turned out to be wrong. but still, like, it turned out to be helpful. Like, that's the first way people managed to prove that all planographs are 5-colorable. And even in a proof of the four-color theorem, you still use Kempe changes in a way to simplify things. Like, it's not necessary to do it, but it just makes your life easier to use them. And, well, simplifying the proof of four-color theorem is really, something you like to do. So any way to do it is good. So since, it was interested for the four-color theorem, but there's still like lots of questions which arise around how you can navigate the space of colourings through Kempe changes. So let me say a few words about that. So initially, not initially, but usually when you first hear about coloring a graph, one of the first parameters which is related to chromatic number, to the number of colors you need for the graph, is the max degree in the graph. So the maximum number of neighbors a vertex can have. That's something we usually denote delta. And by the way, I should mention that throughout this talk, I'm almost always going to drop the parameters. It's delta of G technically, but like there's never any ambiguity in this talk. So, it makes for lighter formulas. So you have the max degree of a graph, that's delta. And you can see trivially, using just a greedy algorithm, that every graph is delta plus 1 colorable. So, delta usually comes as a trivial upper bound on the number of colors you need to color a graph properly. And the way you need to see it, I know I'm starting very slowly, but I promise it's going to get more interesting as time goes. It's just to make sure, everything is clear at the beginning at least. So the way you do it is you just order your vertices arbitrarily, and you're going to process them from left to right. And whenever you look at a new vertex, you're going to give it the smallest color available, the smallest color which is not used on its neighbors. And the number of neighbors it has is at most delta. So you always, the number of colors you use is at most delta plus 1. So that's easy to see. But what's perhaps a little less obvious is that actually all such colorings are Kempe equivalent. So I'm just going to do a small drawing. I find that, when we give proofs online, we tend to always go too fast. And I find that having to draw stuff by hand actually forces you to slow down. So here's a proof by hand that when you take a graph, all its delta plus 1 colorings are Kempe equivalent. So I'm just going to do it by induction. I'm going to take a vertex. It has some neighbors, presumably. So that's the neighbors, and then you have the rest of the graph. So I'm going to delete that vertex. Prove by, use the induction to say that in the rest, all delta plus 1 colorings are Kempe equivalent. And then I just to justify how I'm going to add back that vertex. So the idea is, what could go wrong? Like how could this vertex be an issue? So the kind of issue you could have is if you have if you have one neighbor colored 1, and you perform a 1-to Kempe swap there. So if your vertex is colored something which is not 2, everything is fine. Like, you do the Kempe swap, it does not have any impact. No worries. So what could go wrong is this vertex is colored 2, because then it belongs to the Kempe chain. So it's going to, be included in the Kempe swap. So if it does not have any other neighbor colored 1, it's still not an issue. Sure, its color changes from 2 to 1, but it doesn't ruin the game for the rest of the graph. So we don't really care. What could go wrong is if it has another neighbor colored 1, and then perhaps that guy has other neighbors colored 2, and so on, which means that now if you do a Kempe swap, when you do the Kempe swap on the left, it actually impacts through this new vertex. It actually impacts something on the right which you did not want to impact. So that is an issue. Actually, that's the only issue you can have, but that's kind of a big issue. But this is something you can fix very easily. You're just going to observe that, well, you have delta plus 1 colors total, and you have delta neighbors here, but 2 of them have the same color. So you really only have delta minus 1 colors using your neighborhood, which means you can give your vertex a new color. which is not going to impact the, which is not going to interfere with the 1-2 Kempe swap. So that's like an easy way to just say, well, okay, so then by induction, I can prove whenever I have a graph and whenever my number of colors is at least delta plus 1, all colourings are Kempe equivalent. And one thing you can observe here is that with exactly the same proof, you can obtain that whenever you have a graph which is k-degenerate, all colourings using at least k plus 1 colors are Kempe equivalent. So I'm not sure all of you are familiar with the notion of k-degeneracy. So it's kind of like, having max degree delta, except that you take some ordering of the vertices and everyone should have at most k neighbors to the left. So in other words, you can get rid entirely of the graph by finding some vertex that you get most k, deleting it, and proceeding. So this is a bit like this proof. It's super simple proof. It's a bit stronger than just saying, yeah, all delta plus 1 colourings are equivalent, can be equivalent. It says, yeah, whenever you have enough flexibility in the degrees of the vertices, I mean, as long as you have always a vertex of small enough degree, then all your colourings are going to be Kempe equivalent. Okay, I hope that's fine with everyone. So what more could we say about coloring? So, fine, we were able to say every graph is delta plus 1 colorable, and actually all such colourings are Kempe equivalent. So usually the first thing you learn about after that is that, so I'm trying to, yes, good. Sorry, the first thing you learn after that is that most of the time you can save one color among this on this one of delta plus 1. So namely, what you can prove is that if your graph is neither clique nor not cycle, naturally delta colors are enough. That's a super old theorem as well. I mean, it's not as old as the question of Fogel theorem and stuff, but it's still like from 1941, so fairly old. And we have tons of these different proofs of it. So I think there's even a nice survey about all independent, completely different ways of proving this theorem. So it's a theorem we understand very well. When you have 5 disjoint proofs of the same fact, usually it means you have a fairly good understanding of why that is true. So if you see the pattern here, clearly the next question you should ask is, okay, are all delta colourings always Kempe equivalent? So now we know in all graphs, I mean, in every graph which is not coloring, not a clique or not cycle, there is a delta coloring. As I said, we understand very well why that is true. We have many different proofs that that's the case. So it feels like it's reasonable to think that all of them should be Kempe equivalent. It's a very nice claim, like a very satisfying claim. You have tons of them. Can you at least say, that they're all the same up to Kempe changes? And the thing which is annoying about this conjecture is that it's not true. So this simple graph actually was the counterexample was found much later than the conjecture, like 8 years later. And it's a very simple counterexample, and I'm going to spend some time on it because it's important for the rest of the talk. So how do you argue that 2 colourings are not Kempe equivalent? That's actually hard. Like, what's a good criterion to say that 2 colourings are not Kempe equivalent? So far, the only criterion we have, and that's kind of sad, but the only criterion we have is saying that 1 coloring out of the 2 is something we call frozen. So by frozen, I mean that whenever you look at 2 colors, so say here red and blue, the subgraph induced by that in the graph is connected. And that's true for every pair. You can check red, green, green, blue, they're all connected. So what this means is whenever you do a Kempe swap, you don't change the color partition, meaning 2 vertices which have the same color to begin with will always have the same color. And conversely, if they have a different color to begin with, they will forever have different colors. So you know that Kempe changes cannot allow you to escape that. So if you can just agree there's a different coloring, meaning a coloring with a different color partition, now you know not all such colourings are Kempe equivalent. So it's a simple criterion, but that's the only one we have so far. Like, we don't know of an example where it's not connected, and the reason is not something frozen. So I mean, I'm laying a little bit here in the sense that you can build some cases where the coloring itself is not frozen, and still like the colourings are not all Kempe equivalent, but when you look at it closely, you can see that the reason why it's not Kempe equivalent is because of some frozen coloring in some related graph. Like it's always some frozen reason for every example we have. So yeah, here you can check, you have two different colourings. I mean, they have not the same color partition. I mean, you can check that there are some vertices which have the same color in one and not the same color in the other. And the left one is frozen. Actually, both of them are frozen, but it doesn't matter. I mean, you only need to argue one of them is frozen to get that not all three colourings of this three-color graph are Kempe equivalent. So that was bad news. Not happy to see that there's this nice conjecture which feels like it should be true and it turns out to be false. I forgot to mention, but do feel free to interrupt me if anything is unclear or you have a question or anything. We have plenty of time for all the questions you like. Yes, so that was bad news for the conjecture. But there is some better news, which is that actually if you look at graphs with max degree at most 3, that's the only one which is annoying. And that was kind of a surprise. So it's not very hard to check that it's the only one which admits what we call a frozen coloring, meaning a coloring where you can't escape the color partition through Kempe changes. But it was a surprise that you could actually prove formally that for all the other graphs, you can always do Kempe changes and navigate the space of 3 colorings without any issues. So when you see that, I mean, for us, the main question was, okay, how do these exceptions behave? Like, do you suddenly get infinitely many when you increase the max degree, or do you still get 1 for every value of delta, or how does it behave? And the thing which was kind of funny is that there is no other counterexample. So you have this weird 3 prism, and that's it. For all the other graphs, all the delta colorings are Kempe equivalent. So I mean, Mohar's conjecture that all delta colorings of any graph are always Kempe equivalent, it's technically false, but it's so close to being true. It's frustrating. It's just just this one graph, and the proof is really not that bad. I mean, if you really want to prove that for every single graph other than 3 prism it works, then it's a bit of work. But if you just want to convince yourself that for every fixed delta, there's a finite list of exceptions, it's not too bad. I mean, I can say a few about this at the end if anyone wants to hear. But yeah, it was a quite a big surprise. So yeah. So far, I've only told you about positive results or negative results. But one thing you can also wonder is how many steps do you need? Like how many Kempe changes do you need to go from one coloring to another? And all the proofs I've told you so far, I mean, even the first one, with the graph is given max degree and deleting vertex and stuff, which was a very basic, simple proof. If you think about how many changes that could require, it's actually the bound you get, the upper bound you get is really exponential in the number of vertices. Like it's a very simple proof, but the number of changes could really explode. So that's not very satisfying. And for a very long time, for this proof, saying that all delta colorings of any graph are Kempe equivalent, like we knew there was some sequence. I mean, there's some series of Kempe changes you can do to go from one to any other, but we didn't know how many one it did. And what we proved very recently with a colleague from Bordeaux and a PhD student in Bordeaux, Clément Legrand, is that actually the number of Kempe changes you need in that case is really small. So it's actually quadratic in the number of vertices. And actually we think it should be linear, but that's actually surprisingly hard to prove. I mean, it doesn't seem like it's within reach, even in some simple cases, but it still feels, the real answer should be something linear in terms of number of Kempe changes. So yeah, so that's, if you look back to the history of colorings, there was this trivial delta plus 1, and sure, you can extend this to Kempe swaps, Kempe changes, and then there's there's Brooks' theorem saying delta is enough, and then with quite a lot of work over many years, you can prove that it extends to Kempe changes as long as you allow for one exception. So it feels, now what can you do when you have fewer colors? It seems like, you should be able to get more, like, follow a bit more closely the results in graph coring in general. And actually, you can't say much yet. So something I forgot to say is that looking at Kempe changes is something that's interesting, not just, from a pure theoretical point of view, because it's nice to understand how corings relate, but it's also something which actually comes up in some other settings. So there are some cases in statistical physics where they have some protocols which rely on corings being Kempe equivalent. So it was kind of funny, when we first proved this result saying that all data corings of a graph are Kempe equivalent, we really did not expect that it would have corollaries anywhere. Actually, we were very surprised in to hear that our result actually was interesting to some people in statistical physics. So yeah, usually it's the other way around, right? You lie saying your results could be very useful, and it's actually not very true. And this time we were not. We are just saying, we think this is cute, and it turns out it actually was also useful for some other stuff. That was weird. Anyway, so what I wanted to say earlier is just that this is really baby steps when you compare to the history of graph coring. We're just struggling to get that all data corings of a graph are Kempe equivalent. And as soon as you have fewer colors, then there's so little we can say. I mean, there are some weird behaviors around there, essentially. So, do you have any questions so far? So let's go back to why Kempe changes were introduced. So it was for planographs. So you have this, I mean, now we know it's true that every planograph is four-corable. And how does that behave with respect to Kempe changes? So I mean, initially the hope was kind of, starting from a coring with more colors and like kind of get rid of colors to get down to a four coring. And what we can prove, not we, but what was proved, is that at least whenever you look at a planograph, whenever you look at all k corings of a planograph with k being at least 5, they're all Kempe equivalent. So it's kind of funny. It means, in a way, if you give me like some k coring of a planograph with k a lot bigger than 5, just through Kempe swaps, like I can, get rid of some colors and get down to not just some 5 coring, but my favorite 5 coring. And even if I'm not allowed to use any extra color, I can still go from any 5 coring to any other through Kempe changes. And that does not extend to 4 colors, because when you can find some planographs, and even some 3 connected planographs, so graph where you're not just gluing some copies of that. So you can find some planographs where the number of distinct 4 corings, by distinct I mean that they're not they are pairwise not Kempe equivalent, is exponential in the number of vertices in the graph. So it's really planographs are very far away from being 4 Kempe equivalent. Yes. So now you could think, okay, I see the pattern. Whenever you have, I mean, getting that all chi coring. I mean, if your graph is k corable, it can be hard or even false to prove that all k corings of the graph are Kempe equivalent. But it looks like so far having just one more color is enough to navigate from any coring to any other. It's actually completely false. I'm going to give you a small example. So I could not draw it entirely because it's a messy graph, but I'm kind of drawing the complement. So let me describe it to you. So you choose some parameters L and P, with L being smaller than P. I mean, that's going to be relevant to make sense a bit later. And you choose LP vertices and you display them on a grid. And what you're going to say is that every vertex is adjacent to every other vertex which is on a different line and a different column. So every line sorry, every line indices a stable set, and every column indices a stable set. But yeah, whenever you take vertices which are on different lines and different columns, they are adjacent. So it's kind of the complement of the picture here. I mean, if you try to draw in the complement, you'll see it's impossible to look at. So that's why I drew that one. But really, it's the complement which I'm interested in. So what's interesting in that graph? So what's interesting is that because I mean, as I said, every column is a stable set, and every line is a stable set that gives you a natural coloring. So clearly, you can find an L coloring. I mean, if L is the number of lines, just by giving one color to each line, and you can also find a P coloring where you have like one color for each column. So the chromatin number of your graph, meaning the number of colors you need, I mean that's enough to color the graph. It's just the number of lines in it. But if you look at the coloring given by the columns, so again, just giving one color to each column, what you can see is that it's frozen again, because I mean, assuming L and P are large enough, but whatever. So if you look at the blue and the green, when you look at subgraph induced by it, you can check it's connected because every blue vertex is adjacent to all the green vertices but one. So it's very connected. So when you start from this coloring, I mean, from this coloring given by the columns, it's frozen. So this means that you have a graph where there is no function of the chromatin number that will allow you to navigate the space of colorings. And what's extra nice about this example is that the corresponding graph, I mean, it's kind of hard to check. You have to trust me on that, I'm afraid, is that it's perfect. You don't have any odd hole or odd anti-hole. So it means that we have a graph which misbehaves badly with respect to Kempe colorings. And it's even supposed to be a nice graph for colorings. I mean, that's perfect graphs are, some of the nicest graphs you can think of for graph coloring. And well, this shows that they're not nice for Kempe changes. So that's kind of, bad news. So for Planographs, things behave quite well. We can't quite argue that all 4 colorings are Kempe equivalent, or even that every 5 coloring is equivalent to some 4 coloring. But at least you can argue that all 5 colorings are Kempe equivalent, which is nice. But there is no hope whatsoever for generation of this to general graphs or even to perfect graphs. And as I said, even with an arbitrary function of chromatin number, there is no, it's completely hopeless to get something like that. You have to use some other parameter or restrict the graph a bit further. So speaking of restrictions, what's one way to generalize planographs? So one way, I mean, there are many ways really. I don't want to talk about graphs and surfaces or anything. I want to talk about minors. So what's a large clique minor, or just a clique minor? So it's just, I mean, you say your graph contains a clique of size t as a minor. If you can find t disjoint blobs where each blob is connected, such that when you shrink them, you obtain a clique. Meaning between any 2 blobs, you have at least 1 edge, maybe more, maybe less. Oh no, not less than 1, but I mean maybe more, and that's fine. So another way to define minors is something you obtain from the initial graph through a series of deleting a vertex, deleting an edge, or contracting an edge. Hope the definition is clear to everyone. And one thing you can check is that no planar graph contains a K5 as a minor. If you're planar, there's no way you can build a clique of size 5 through vertex deletion, edge deletion, or vertex contraction. Just because, I mean, you can't draw K5 in the plane without edges crossing. And one of the reasons why minors are interesting for coloring, well, there are many reasons, but anyway, one of them is that there's this nice conjecture by Hedviger that if you have a graph with no large clique minor, then it has to be colorable with few colors. And this is the exact conjecture. So if you don't contain a clique of size t as a minor, then it should be t-1 colorable. So I'm not sure how intuitive this is to you, that this should be true, or that this makes sense as a conjecture. But essentially, the reason why we look at clicks minors, not just directly clicks or some other structure of the graph, is because essentially every structure which is more restricted than a minor actually turns out to be false as a way to bound the chromatic number. So in a way, this is the most restrictive condition we can think of in that direction for a graph to have small chromatic number. Yes, so there's this conjecture, and as I said, you take T being 5, that's a stronger statement than the four-color theorem. Because if you take T being 5, it says any graph with no K5 minor is four-colorable, and every planar graph is a graph with no K5 minor. So it's a lot stronger. But still, it's proven in that case, actually it's proof for a little bit stronger than that. So it's also proof for T being 6. And the proof is also super technical, super hard. But it's very nice. And as soon as you take T being 7, you have partial results, but not the whole thing. So for T being 7, it's true. We know it's true by 1 off, meaning we know it's every graph with no K7 minor is actually 7 colorable, but we don't know yet that they're all 6 colorable, which is a bit sad. It's not clear if this conjecture should be true or not. I mean, it does hope that at least it should be true, at least with some factor, but it's not clear that it should be true with exactly T minus 1. Anyway, that's a story for another time. Yes, so you have this old conjecture, which, well, as I said, is super hard. And again, you can try to look at it from the point of view of Kempe changes. So we don't know if any such coloring exists, but what we can do is imagine there are some, and think about how they relate to each other. So there was this nice conjecture by Lasvanias and Meniel from 1981, saying that if you allow just one more color, all the colorings should be Kempe equivalent. So it's kind of a weird conjecture. Like it does not imply Hadwick's conjecture, and Hadwick's conjecture does not imply it, but it's kind of in flavor similar to it. So again, it's not saying there should be a T coloring. It's just saying that whenever you look at a graph with no KT minor, all its T colorings, maybe there are none, but all its T colorings should be Kempe equivalent. And here again, it's been confirmed for some small classes. So it's not trivial how to extend the proof for planographs to K5 minor 3, but still it works out. I mean, it's quite a few pages of work, but it works. And it's completely open for higher T. I mean, it's also just needed a lot less attention, but yeah, it's an interesting conjecture. So I used to think this conjecture was true. Like it made sense in a way. Like at least if you have a frozen coloring, meaning if you have a coloring where you can't escape through Kempe changes, it made sense to me that yes, there would be enough blobs that you could connect through path and stuff and through edges or whatever. Until actually earlier this year, we proved that this is very wrong. So what do I mean by very wrong? I mean that the factor is wrong. So it's not just that you can find a graph where the T colorings are not concurrent, but all T plus 1 colorings are. It's really that essentially for this conjecture to be true, you need at least 3/2 as many colors. That's the only hope. And it's not clear, it's going to work out with that. But what we know is if it's going to be true, you need extra half in the number of colors. I'm going to say a few more words about the construction behind this in a moment. But I mean, one subtlety here is that we really need very large T for this to be true. So yeah, I mean, I'll come back to this in a bit. So what's behind this construction? So it's related to something called quasi-minors. I'm going to define quasi-minors, but essentially they had a weaker conjecture, which I'm going to rephrase a little bit in this way, saying that if you have a graph with no KT minor, then it shouldn't have any frozen T coloring. And you have this, you have notion of quasi-KT minor, which is something a little bit more general. But whenever you have a frozen T coloring, for sure you have a quasi-KT minor. That's all you need to know. And this weaker conjecture, so you're really just saying I mean, not saying that all coring should be equivalent, but just saying there is no frozen coring, which, you know, is the base step towards getting that they're all equivalent. It was proved to hold for a surprising high number of cases. So, you know, initially when they proved the conjecture, sorry, not the proof, when they posed the conjecture, they already confirmed that this should be true for T atmos 6, and then there was like T atmos 8, 1994, and T being 9, 6 years ago, something. No, 15 years ago. Anyway, and then lately, actually, just last year, T being 10 has been confirmed. Actually, the proof of that one is really nice. It's just a short note on the archive if you want to check it. It's quite nice. And it's a lot simpler than the previous cases. I mean, for the previous cases, it's quite a lot of hard work. So yeah, this note is very welcome as a way to understand, you know, what's the link between having a frozen T coring and for sure having a large click minor.
Does it rely on the previous cases?
No, he completely reproves it, I think.
Okay.
As far as I remember. Actually, I wonder if he's not using some lemma in one of those. But anyway, he does not just use the smaller case. Perhaps he uses some external tool, but it's not just restricting to smaller case. So yeah, and so what we prove is that, I mean, as I said, you can find graph with no KT minor, which has essentially a frozen almost 3/2 T coring. And before I tell you about the exact construction, what you can wonder is for which factor in front of the T that should be true. So in other words, if you have a graph which admits a T coring, what's the smallest T such that you can guarantee it contains a KCT minor? And it's very easy to check that half of T works for sure. Just because, I mean, you take you pair colors. So you can say, you know, colors 1 and 2 from one blob, colors 3 and 4 from one blob, and so on. And this builds you like a K half of T minor. Just because it's frozen, so for sure you have a net between, you know, color 2 and color 3, color 3 and color 5, and so on and so on. And the point in pairing colors is just make sure the blob is connected. I mean, if you take colors 1 and 2, by assumption, since it's a frozen coring, it misses the connected graph. So that's just the point in pairing. And what we proved is the best you can hope for is 2/3. You cannot go above that. I mean, the conjecture by Lajones and Méniel was that you should be able to take C being precisely 1. And now we know the best you can hope for is 2/3. And it's really not clear what's the right answer. Like we actually spent some time trying to think about it, like how to extend a construction, which I'm going to describe in a minute. But we spent some time trying to see what should be the answer, and we don't even have a conjecture. Some days we feel it's one, some days we feel it's the other, and that's weird. Anyway, so you know, once we know what happens for frozen coring, so as I said, for frozen, we know like it's just a matter of finding the right constant in front of the T, but we know there is one. I mean, we know half of T works for sure. But if you think about the much wider conjecture about, you know, whether they're all Kempe equivalent, then nothing is known in terms of having some constant time T being fine. And as I said earlier, it's very frustrating because so far the only way we have of arguing something is not connected, I mean that two corings are not Kempe equivalent, is by saying that essentially one of them is frozen or is frozen in some sense. And in this case, it's kind of interesting because having a negative answer to this would mean we found some new tools proving that, I mean, some new tools to argue corings are not Kempe equivalent. And I would really love to see that. I think I'd be actually happier with a negative answer than with a positive answer. Of course, I'd be happy with either. And one thing I should mention is that even though it's completely open, if you can get some constant time t, whenever you have a graph with no KT minor, it's been known for ages that you always find a graph with small degree, and by small I mean roughly t log t. and you can delete it and start again. So essentially there are T log T, I mean, that's a constant factor, but whatever. They're essentially T log T degenerate. And so you know that all T log T, roughly, I mean, again, up to factors, whatever, all T log T colourings are Kempe equivalent for sure. But it's really not clear whether you can get rid of, I mean, so we know there is some function of T for which it works and like some reasonably small function of T for which it works, but it's not clear whether you can actually make it linear. So yeah, I thought I should mention this question because I really like it. Okay, so now I can tell you a little bit about the construction. How do we find a graph with no large KT minor, which still emits a frozen coloring? It's actually super simple.
So I have a question.
Please go ahead.
So you're referring to this degeneracy threshold for Hadwigers, and if the graph is sufficiently degenerated, then your Kempe swaps work with this easy argument you showed at the beginning.
Yes.
But there is, as you know well, there is this
recent progress by
recent progress. Yes. The question is if it applies in any way to Kempe stuff.
No, it doesn't. So the reason essentially is because when you do Kempe, almost all things you do with colourings are illegal. So, I mean, in some sense, like when you just try to find a coloring and you start with a blank graph, you can say, I'm going to use this set of colors for that part of the graph. That's something you can't do for Kempe changes because, I mean, you need to be able to argue that you can, through Kempe swaps, kind of, move all the colors of that set to this part of the graph. And that's something that's hard in general. I mean, I didn't spend very long trying to extend their proof to Kempe swaps, but essentially, it's the kind of operation which does not behave well with Kempe swaps. But yeah, there's it would be nice if it did. I mean, one thing I find interesting about Kempe swaps, in some sense, is that it gives you a measure of the kind of tools you need to get something. Like the only cases where you can prove that all black colourings are Kempe equivalent are when the reason why you have a small colourings are very simple, in a way. So, I mean, of course, I like just seeing how the colourings behave, but I also think it's yeah, as I said, a measure of the kind of way you need to think about the colouring problem, if that makes sense to you. Yeah. So so we want to prove that you can go arbitrarily close to 3/2 as a factor. And sorry, let me start again. That when you have a graph with no KT minor, you might need arbitrarily close to 3/2 T colors to have a hope for Kempe equivalence actually that there are. I mean, so formally for any positive epsilon, as soon as your T is large enough, you can find a graph with no KT minor, which admits a frozen 3/2 of T minus epsilon T coloring. And I mean, then you need to argue that's a different one, but that's easy. So how do you do it? So take some P, large P, consider a clique on that many vertices. So now what you're going to do is blow up every vertex into just one pair of 2 vertices. So now what you see between any 2 vertices, I mean, and 2 former vertices in the clique is going to be this. So every vertex is now a stable set of size 2, and you have, well, all 4 edges with to any other pair. And now just to do one easy operation is that for every pair, uniformly at random, etc., you select one edge out of the 4 and you delete it. That edge was chosen at random, I promise. And then you think about what's the resulting graph. So what can you say about the resulting graph? Essentially, every edge is every edge of the initial graph, meaning before deleting a random edge, every edge stays with property essentially 3/4. So, I said you replace every vertex with one pair, so you can call them the BIs and the CIs just to distinguish the two vertices in the pair. In some sense, if you look at the graph induced by the BIs, that's essentially GP 3/4. And same for CIs, except the two processes are not independent. But essentially, whenever you look at one slice of the graph, that's essentially Gn 3/4. I mean, I find it useful to keep this in mind to understand what's going on in the graph. And the idea is, when you do this, when P is large, you can prove that there's a really good chance that you're not going to find any minor of size a bit more than 2/3 of P. And one thing you can check is that she still emits a frozen P coloring. And the way to have a frozen P coloring is a silly way. Just like for every initial vertex in the clique, which is now, well, 2 vertices, you give 1 color. So here, the BI and CI we call it I, and BJ and CJ would be called J. And when you look at the component induced by colors I and J, that's a P4, so it's connected, so you can't escape the coloring. And essentially, to prove that there is no large minor, what you can see, just to have some intuition, what you can see is already there is no large clique. Because essentially, I mean, as I said, every slice is a roughly Gn 3/4. It means that largest clique is, well, roughly log P, so we can essentially ignore it. If you have a large minor, it means, every bag, every blob is going to contain at least 2 vertices. And just because you don't have so much room, you really can't have that many blobs containing 3 vertices. So you just need to argue that the chances of you getting a non-negligible minor, by non-negligible I mean roughly epsilon P, probability of getting a minor of size, a clique minor of size epsilon P using just blobs of size 2 is really small. And that's not very hard to do. Again, you can do it in each slice. I mean, you can argue that it suffices to do it in just each slice, and things just work out. Actually, the note is on the archive, and the proof is very basic. Actually, we checked it tons of times because we felt it was too simple, that there had to be a trap. But I don't think there's a trap. I think that's it. That's how you can prove that the Hadwiger signature does not extend very well to Kempe changes. I mean, even in the frozen setting. Yes. So that's it for stuff around Hadwiger signature. So there was this thing, with Planographs it works well. We know that for perfect graphs it's not going to work well. But we have kind of a hope that in some other settings it could work. So we had this hope for a graph with no large clique minor, but that turns out to be at least partially false. I mean, at least we know it's false by some constant factor, which it's not that bad news. It just says it's going to be harder than not harder, but it's going to be a slightly more confusing picture that than you could expect. Let's think about some other case where you could have something weird happening. I mean, when we don't know very well what happens for graph coloring, but we can think about what happens for Kempe changes. So here's the conjecture I really like. So it kind of goes back to the start of this talk when I said every graph is trivially delta plus 1 colorable. So that's a trivial upper bound on the number of colors you need to color the graph. That's a trivial lower bound, which is related to omega, which is the size of the largest clique in the graph. I mean, of course, if you have 10 vertices which are all pairwise adjacent in your graph, you're going to need at least 10 colors. That's a trivial lower bound for the comet number. And what Ritz's conjecture is about is just saying that the real number of colors you need is closer to the trivial lower bound than to the trivial upper bound. So formally, exactly this. So you take the average of the two, take the ceiling for technical reasons, and that should be an upper bound on the comet number of your graph. So this conjecture is widely open still. That's that's frustrating. I mean, it's been proven in some cases. And say a few more words about this. Yes, so the kind of thing which is known, I mean, you can try to find a worst trade-off between trivial upper bound and trivial lower bound. So I mean, clearly, if you do a trade-off of 1 and 0, sure, every graph is delta plus 1 colorable. It's really non-trivial to get to a 1 minus epsilon and epsilon. Actually, to do this, you need something. I mean, you need the probabilistic method to get that. That was from the same paper, I think. Reed proved that there is some small trade-off you can have. And then there's been a series of papers, every 2 years, the epsilon is multiplied by 2. And currently, this is the best trade-off we have. It might not look like much, but it's getting so much closer to the actual pointer than it used to be. So I like it. So it's roughly 1/8, something like this. Anyway, I'm not going to try to convert this into fractions right now. But anyway, the point is, we don't know much about this conjecture yet. What we know is that we can do some trade-off. Actually, the trade-off we can do is not that bad. Like actually, we can trade off quite a big chunk of the trivial upper bound for the same chunk of the trivial lower bound. And one thing I should mention is that this conjecture is actually tight. So how do you prove it's tight? I'm all going to draw some stuff. So take C5. It doesn't look like it's C5. And blow up a vertex into a clique of size P. So what do I mean by this? I mean that, well, so every bag I draw is a clique on P vertices, and you have all possible edges between consecutive bags. Right? So this is the graph. And every clique is of the same size. So if we have everyone being of size P. And so roughly what you can check is that, well, delta is order 3p, omega is order 2p. And how many colors do you need? Well, if you look at one given color, how many times can it appear in the graph? So it could appear twice. For example, like you could have, say, one vertex being called red here and one vertex being called red here, but you couldn't have a third one. So every color is used at most twice. So the number of colors you need is at least half of number of vertices, which is 5/2 of P. And again, delta is roughly 3P, omega is roughly 2P, and number of colors we need is roughly 5/2 of P. So we know we can't get, so we were wondering, what kind of trade-off we can have between trivial upper bound and trivial lower bound. And this construction shows that you can't trade off more than a half. So that's why risk nature would be tight if it's true. So it's still, yeah, very much open again, but yeah, I guess I just like this construction. So this is just from the point of view of just normal coloring. You have the graph, and you're just trying to give colors to it, which is a lot easier than swapping colors around and trying to see what happens. So what happens if you try to do that? Let's look at it. So you could try to hope that for any graph, if you take that many colors, then all scorings are equivalent. I mean, actually, there's hope you would be able to prove this, even if you still fail to prove risk nature. Because again, I mean, you'd be assuming you have such scoring. So that's fine. So if you think about the previous construction, so again, like having this large clique and blowing up a vertex into just one pair, deleting a random edge between every pair. So what did you have? You had a frozen P coring. And remember, P were the number of cliques initially, I mean, from when we start the construction. And largest clique number is tiny, really tiny. It's negligible. And I didn't discuss this initially, but what you can check is that delta, well, the expectation of delta is 3/2 of P, because for every vertex, for every pair, you get property a half of having degree 2 and property a half of having degree 1. And it's very easy to check that. I mean, the events are independent enough that you can actually reach pretty much that much for the max degree. So max degree is roughly 3/2 of P, omega is negligible, and you have a frozen P coring. So what this means is that if you're going to get anything like this, you need not half of that, but at least 2/3 of that. Just because, again, of this in construction, which turns out to be really annoying as far as Kempe changes go. And it's not clear at all whether 2/3 should be enough. No idea. Maybe it's true, that all 2/3 of that corings are equivalent in any graph, but yeah. there are lots of open questions left. So I'm hoping some of you get inspired by some of these questions. Yeah. So we had this Hadwiger signature, and we see that things do not extend to. I mean, even if we still don't know what happens for graph coloring, we know things do not extend to Kempe changes. And for risk signature, same story essentially. So again, it's only false by some factor, but I mean, we know it's true for just delta plus one. So the factor here is important, even though it might not be super important for Hadwiger signature. Here, factors matter. Anyway, so let me tell you about something completely different now. Still recurring, but things from a different point of view. Oh yeah, sorry. So just saying, yeah, you need 2/3 if you're going to go for a Kempe version of that. So I want to tell you about. Sorry, I'm just deleting my drawings. Yes. Okay, sorry. I told you so far about just Kempe changes for the sake of Kempe changes. Just because we like it, we're going to tell you about how you can navigate the space of colourings through Kempe changes. But it's also a tool to some extent, Kempe changes. I mean, initially the reason why Kempe introduced them was because he wanted to prove the Fokker theorem, and he felt that Kempe changes could be helpful. And here is a theorem where you need Kempe changes if you're going to prove it. I don't know of any proof where you can get away from it. There are some proofs where you cannot hide it, but it's still there. So let me tell you about it. So Wissing's theorem. If you know, I mean, if you've worked on coloring, you probably know Wissing's theorem, but I'm still going to explain it to you. So you have a graph, you're coloring the edges of the graph. And the question is, how many colors do you need to do that? So we can do kind of same thing as before and say, okay, what's the trivial lower bound? So clearly now a click in the new graph, that's actually a vertex plus high degree in the initial graph. So you have a vertex with 10 incident edges, that's 10. You can check you need 10 different colors. So if you denote chi prime the number of colors you need to color the edges of the graph, you need at least delta colors to do that. And if you look at the trivial upper bound, which was max degree plus 1, well, what's the max degree in the line graph? So when you color the edges, how many instant edges can you have to one single edge? Actually, the answer is twice delta. So if you do it naively, and if you color things greedily, you're just going to get a roughly 2 delta coloring. But Wissing proved many years ago now that, well, you don't need to be stupid. You don't need 2 delta colors. You can actually be very close to delta. You can prove you always obtain at most delta plus 1 coloring. Actually, deciding which of these 2 values is, I mean, is the right one, that's NP hard. But still, it's super nice that here, well, we only have 2 options. It's either this or that, and that's it. It's something we really don't have for vertex coloring, but at least here things work well. And essentially, the reason it works well is because of Kempe swaps. So yes, I said that it's crucial for the proof of that. And just to be on the same page, Kempe swaps among edge colorings, that's the same thing as for vertex colorings, except you do it on edges. So there's no trap here, but still here you have exactly the same picture as for vertex, but just doing it on edges, and you can check that's still completely fine. You still navigate the space of K colorings, K edge colorings through Kempe swaps. So what he proved really is that if you start from your favorite graph and you start from an arbitrary edge coloring, proper edge coloring, then through a series of Kempe swaps, you can always get down to a delta plus 1 edge coloring, for sure. No matter which graph you start from, no matter which edge coloring you start with, you can always end up with some proper delta plus 1 edge coloring. So how do you get rid of colors? Because I mean, when we do Kempe swap, we just swap colors. So it might feel to you that that's not one way you can get rid of colors. But actually, if you have a you're trying to get rid of color delta plus 2, say. So you find an edge called delta plus 2. And if you see, say, color 1 does not appear in the instant edges, then you do a delta plus 2, 1 Kempe swap, and you've decreased the number of edges being called delta plus 2. So that's essentially how you can decrease the number of colors involved in the edge coloring. And that's almost exactly Wissing's proof, except that you need to do a little trick to make sure there is some small color available around one given edge which you want to recolor. But if you don't know about how to prove Fielding's theorem, well, you should look it up, but also you can ask me and I'm very happy to sketch the proof. It's actually very simple. Well, okay, maybe a warm-up exercise is do it for bipartite graphs. And then things are easier. Actually, for bipartite graphs, you can get the delta H scoring, but anyway, that's another topic. So yeah, so you can prove this theorem using Kempe swaps. Actually, you need to use, not really need, but the only way so far we know how to prove it is through Kempe swaps. And one thing which I find really intriguing around this is that just a year later, he conjectures that actually you can do better. So, I mean, true, from any scoring, you can reach delta plus 1, 1. So you know the number of edges you need to color the number of colors you need to color the edges of the graph is at most delta plus 1. But he conjectured just the year after that actually if your graph admits some delta edge scoring, then you should be able to reach that through a series of Kempe changes. You might not be able to control, which delta edge scoring you end up with. Just like, in his initial theorem, you don't necessarily control what kind of delta plus 1 edge scoring you end up with. But his conjecture is that you should always be able to get down some optimal edge scoring. So it's only interesting. I mean, not interesting. It's been proved for all cases except for the one where you have a graph which admits delta edge scoring, and you have specifically delta plus 1 colors left. So you have a graph which admits a delta edge scoring. I give you some delta plus 1 edge scoring. Can you, through a series of Kempe swaps, get rid of the color delta plus 1? So that's very widely open. It's been confirmed for subcubic graphs and more recently for graphs with max to get most 4. And one thing which was proved 10 years ago is that for bipartite graphs, it's true. Actually, proving it's true is not very hard. But one thing which is a bit more interesting is that in a bipartite graph, all delta plus 1 edge scorings are Kempe equivalent. So it's not just that from a delta plus 1 edge scoring, you can reach some delta edge scoring. It's that you can reach your favorite one for bipartite graphs. And what we proved recently with Oscar Defrin, Patka Krimoshova, Willy Lagut, and Jonathan Arboni is that for triangle-free graphs, that's true as well. Meaning, actually, this is interesting for both cases. I mean, both for the case where you admit a delta scoring and the case where you don't admit a delta scoring. Regardless of the scenario, as soon as you have one more color available, you can get down to your favorite optimum scoring. And the proof is not that bad. We essentially just using Fielding's proof and kind of tweaking some things so that you can get some extra freedom. Yeah, I'm happy to say more about this if anyone is interested about the specific thing, but I did not put slides on that proof here, but actually I have slides where I explain the proof, so I'm happy to pull them up if you like. So it's kind of interesting because it's kind of hard to understand why triangles should be important. I mean, in the proof, I can see very well where triangles are annoying, but on a moral point of view, it doesn't seem like triangle-free graphs should behave better with respect to that. Actually, we're fairly sure we can replace triangle-free with like diamond-free, where diamond is just well, 2 triangles joined on one edge. But the proof is essentially 20 pages longer. And we still, not completely sure the write-up is correct because there's so many cases and it's so ugly. Whereas the proof for triangle-free is really cute and simple. So, so we prefer to stick to triangle-free because having a nice proof is important. And it's kind of funny because Fielding's conjecture is not just for simple graphs. It's actually also for multi-graphs. So it doesn't matter how many edges you should have between 2 given vertices. Like, it doesn't matter what the multiplicity of your graph is. Start from any proper edge scoring. Through a series of Kempe swaps, you should be able to get down to an optimum edge scoring. And that's harder to believe than the conjecture in simple graphs. Essentially, because as soon as you have multiple edges, it's hard to control what happens, essentially. I mean, I don't want to say too much about that, but that's the very rough idea. Another case which is surprisingly hard is that of planographs. So for planographs, it seems to, that you have enough freedom that here again, whenever you want to recolor one edge, like get rid of some color, it seems like you should always be able to say, if you can't do anything, then there has to be some K5 minor or something. And here again, we tried doing it and we failed. So, I mean, you can use discharging to prove that for some values of delta it works, and essentially you're done with only a handful of values of delta where it's not easy. But that's clearly the hardest one. First of all, when max degree is equal to 6, that's always the hardest part for discharging. I mean, here you can't really say anything, so that's kind of frustrating. So yeah, this proof of this is simple, and it's frustrating to see how little we understand about edge colorings in this setting. Because yeah, Wissing's theorem is very simple, and this test, this conjecture, where you should be able to always reach some optimum coloring, and it's not clear how you can do it, and it's kind of frustrating, that we only know it so far for triangle graphs and graphs with max to get most far. So yeah. So just as a quick conclusion, really what I hope to have convinced you of is that it's interesting to, I mean, just as an insight into colorings, it's interesting to see how they behave with respect to Kempe swaps. Like it's interesting to see whether you can navigate the space well, or you have different components of stuff. And there are many things which frustrate me in this setting. Like there are many things we don't know yet, but the two main things which annoy me, sorry, is for one that we don't have any argument. I mean, I said this before, but it really annoys me. So we don't have any argument to say not all colorings are equivalent, besides saying here's a frozen one. And so yeah, having a frozen one is not enough. You need to say there's a different one. But anyway, that's the only way we have of guaranteeing that not all colorings are equivalent. And it seems there should be other reasons, but it's hard to come up with a good topological argument or something to guarantee that two colorings are not equivalent. And the other thing which frustrates me quite a lot is related to the diameter. I mean, I haven't discussed too much diameters and stuff, but essentially in Wissing's theorem, you get a diameter of roughly number of vertices times number of edges, and something similar in our proof, the triumphal case, getting down to an optimum to an optimum edge coloring. In the vertex setting, we get like as I said, when you look at all delta colorings of graph, you can make sure the diameter is quadratic in the number of vertices. And it feels like always, all the examples we can think of, the answer seems to be linear. I'm not saying it is linear, I'm saying we don't see any reason to think it's not always linear. It's hard to come up with a graph where you can find a path, but the path is not linear. So that's really frustrating, because usually, we struggle just getting some polynomial bound, like some bound which is not just exponential in number of vertices. So it's doubly annoying to see that it seems like maybe the real answer is so much smaller than what we can prove. So yeah, that's the two main questions. And if you have small diameter, one thing you can try to do is have a Markov chain navigate the space of colorings. That's interesting for many different reasons, but the main one for me is that this allows you to sample a random coloring. Because if I give you a graph and I tell you, okay, give me a random k-coloring of it, that's super hard. How do you come up with a random k-coloring? What's a random k-coloring? So you want to select each coloring uniformly at random, and that's there are not many ways you can do this. And one of them is navigate the space of colourings through Kempe changes or, or similar tricks, and prove that fast enough, you get to a random colouring. And to get to a random colouring fast, you need to be able to argue that the diameter is very small. And in particular, it should be, well, linear or close to linear. But yeah, that again seems to be true. It seems that you should be able to sample random colouring very fast, but we don't manage yet. So that's it for my talk. Thanks a lot.
Okay, thank you.